This doesn't render that well on most mobile browsers, so the formulas are hard to read. Instead, you can download the PDF and read that on your cell phones. Okay. Otherwise, does anybody have any questions for me before we start? No? Okay, good. So today is a lecture about an algorithm that fits in well with our topic of recurrences, because it's a recursive algorithm, and it's an interesting one because it's really the prototypical divide and conquer algorithm that is sort of one of the first things we discovered in computer science that is a really general strategy for attacking problems, where you get to use recursion and seemingly, so one nice thing about recursion is sometimes it feels like you didn't have to do anything and the problem gets solved, which is really nice. The other thing about this one is you don't have to really do anything and the problem gets solved efficiently. So we'll take a look at this. And, you know, the problem is sorting. So what you want to do is you're given a list of n numbers. Let's call them A1 through AN. You want to return a list containing the same numbers in sorted order. So you return a list that looks like x1 through xn, but in that list, x1 is less than or equal to x2, is less than or equal to x3, is less than or equal to xn. And these things are the same values that appear in your input list. Okay? Not in the same order, but the same values. Okay? So in particular, in the case of when all the elements are distinct, that's easy to describe as just saying that the set x1 through xn is equal to the set a1 through an. But it can be the case that there are equal values in your list, in which case you want them to appear the same number of times in this one as they appear in this one. Okay? So it's clear what the problem is, the sorting problem. You've probably all used a sorting routine before. Some of you have even probably implemented one. And, you know, every sort of intro to algorithms and intro to computer science textbook will have a couple of these sorting algorithms in it, usually starting with the basic iterative ones, things like bubble sort and insertion sort, and then moving up to one of the nicest and oldest ones, which is the one we're going to study today, and it is MergeSort. So MergeSort takes a list, A1 through AN, and it's supposed to return the sorted version of that list. It's a recursive algorithm. So like inductive proofs, recursive algorithms have two parts. So what's the first part, the one that you should make sure you can deal with easily? Yep.
If the list is of size 1.
If the list is of size 1 or if the list is of size 0. So if n is less than or equal to 1, then, so that means we have either an empty list or a list with one element in it. Is that particularly difficult to sort? There's nothing to do, right? A list with one element is already sorted, and an empty list is somehow trivially sorted. So in that case, we just return. I'll use the notation A1 through AN, but really this is meaning either an empty list or one value. Okay? That's the easy thing to do. Otherwise, we want to somehow recurse, or or apply induction if you prefer. So any ideas how we can do that? Any suggestions? So if we want to do recursion, we want to recurse on something that's smaller. So we have n, which is at least 2, a list of length at least 2. We want to recurse on something smaller. What can we try to do? What's that? Recurse on half the list. That's a good idea. So let's say that L1 is equal to A1 up to A n over 2, and let's take the floor. So this is L1 is the first half of the list. And we might as well give a name to the second half. L2 is A n over 2 plus 1 up to A n. L2 is the second half. All right, and the idea is to recurse on the first half. So let's say, let's give this a name. S1 is what we get when we call MergeSort on the list L1. So we sort the first half. Then what? Might as well sort the second half. S2 for sorted is what happens when what we get by recursively sorting the second half. Now what? Yep. Merge them. So it's there in the name. Merge the two lists. And we'll say, let's return the merge of S1 and S2. Okay? And now we need to define what it means to merge these two things. What we want is some routine that takes a sorted list S1, takes a sorted list S2, and gives us back a sorted list that contains all the elements in S1 and all the elements of S2. Now, why is that a little bit easier, or why should that be easier? Well, that seems like it should be easier than just trying to merge L1 and L2 into a single sorted list, because L1 and L2, those things were not necessarily sorted, but these things are. So let's see if we can design something to merge S1 and S2. So merge the sorted lists S1 and S2 into a single sorted list. All right. Now this won't be a recursive algorithm, or it would only be trivially recursive if you wanted to do it that way. So it'll just be an iterative algorithm. So there'll be some loop in there, but at each step of this loop, so for example, you might have something like S1 is 1, 5, 7, 9, and 15. S2 is 3, 4, 10, 18, 22. And I want to, programmatically merge those things into a single sorted list. So if we start with this example, and we want to write out what is the sorted list that we get, then, well, how would you do it? Yep.
First find the smallest of the two lists.
Yeah. So we know that in the final output list, the final sorted list, the smallest value appears first. And the smallest value across the two sets is either this one or this one, right? Because the smallest value in S1 is the first thing that appears here. That's what it means to be sorted. And the smallest value in S2 is the first thing that appears here. And so whichever one of these two is the smallest is the one that's globally smallest over the whole thing. Okay, so somehow in this code we're going to have something like if, well, let's say x1 is equal to, let's say, first element of L1, x2 is equal to first element of L2, and something like if x1 is smaller than or equal to x2, then, so let's say that the sorted list that we're going to create at the end of this is some list S. So we'll append x1 to S in this case, and we'll, I don't know how you want to call it, but we can say pop x1. And x1 must be bigger than x2, so x2 should be the thing that we use. So we say s.append x2 and pop x2 off of L2. Okay, so somehow this is going to be in a loop that we'll need to figure out, but let's see what this does so far. So this says, look at the first element of S1, look at the first element of S2, whichever one is, see which one is smaller. In this case, it's the first one in L1. So our output list S, it's going to start with a 1, and then we cross that off. We take that off of S1, and now we'll repeat this step. We look at the first element of S1, which is a 5, the first element of S2, which is a 3. 5 is not less than or equal to 3, so we'll take the element of S2. So we get 3, and we cross that off. And now it's 5 versus 4. We take the 4 and cross it off. Now it's 5 versus 10. We take the 5 and cross it off. 7 versus 10, we take the 7. 10 versus 9, we take the 9. 10 versus 15, we take the 10. 15 versus 18, we take the 15. And now we have a problem. So our code is incomplete because we neglected to consider the possibility that S1 was empty, and in this case we got to the thing that S1 is empty. So if this was written in any reasonable programming language, we'd get a crash here when we ask for the first element of L1. Okay. So that says we'd better guard that with something, which is if L1 is empty, then what should we do? Add the rest of L2. So then we would do something like S2 dot, I don't know, in Python you would say extend, S dot extend using the contents of L2, which in this case would take the last two things in S2 and put them on the end of this list. Okay. So it finishes up that way. Okay? Yeah?
So you made a definition of L1 and L2 there. Shouldn't difference be S1, S2?
Oh, sorry. You're right. I should be saying S1, S2 here. S1, S2, S1, S2. So the inputs to the merge algorithm are the sorted list. Okay. Is there anything else missing from this code? Yeah, so here we happen to have an example where we ran out of elements in S1 before we ran out of elements in S2, but it could have been the other way around. And here we should probably do something like, if L2 is empty, then we want to do the same thing. So L2 is empty, but maybe L1 is not. So we take our sorted thing that we're trying to output, and we take everything in L1 and stick it on the end. And we should, it's terrible programming style. So in this case, let's be really ugly about it. In this case, we immediately return S. In this case, we immediately return S because we're done. If we haven't returned by now, then we know L1 is not empty and L2 is not empty. So it's safe to ask for the first element of L1, and it's safe to ask for the first element of S1, and safe to ask for the first element of S2. Then we can do this step here. All right. Somehow at the very end of this, we'll want to return the sorted list S if we haven't done so already. And
Isn't that unnecessary?
well, it depends what we do next. This whole thing should be in a loop somehow. And so what do you want to put for the loop condition? Well, both the lists are not empty, so, or well, one of the lists is not empty, or actually you can actually do this forever. So here's one that I like to use. While 1 is less than 2, then execute this code. And let's convince ourselves that this will work. Well, if L1 is empty, we return. If L2 is empty, we return. Otherwise, we take something away from L1, or we take something away from L2. So eventually, one of L1 and L2 will become empty and will return. So we didn't really need any special condition there. Lots of ways to write this loop. This is just one that we invented today. Okay. But hopefully you're convinced that this procedure, if I give it, as long as I give it two sorted lists, S1 and S2, then it will return a sorted list that contains all the elements of S1 and all the elements of S2. Yeah. Where is this? Oh, yeah, of course. If S1 is empty and S2 is empty. In this function, there is no L1 and L2. Okay. So that's clear. All right. So hopefully we believe, let's say by inspection, that this thing really does, if you give it sorted lists S1 and S2, it merges them into a single sorted list. Now we want to argue that MergeSort works correctly. So we'd like to, I don't know, prove that this algorithm works. How would you prove it? So it's a recursive algorithm. What seems like the natural way to prove it? By induction, and induction on n, the length of the list. So I don't know. Some people really like to do these kinds of proofs, but generally they end up being kind of vacuous and or relying on something like, oh, let's assume that this code works or this code works by inspection. We'll do it, but it's not a particularly enlightening thing. So proof that MergeSort is correct. So the proof is by induction on n, and I'll show you what I mean by being vacuous. Base cases n equals 0, n equals 1 are trivially correct. And what is trivially correct supposed to mean? Well, it's supposed to mean that we looked at the code and saw that it correctly handles those base cases. So that's good. Otherwise, so now we want to assume MergeSort correctly sorts arrays of length 0, 1, 2, all the way up to n minus 1, and prove that it works for arrays of length n. Okay, so let's look at the code for MergeSort, and this is now for n bigger than or equal to 2 because we had the base cases 0 and 1 already. So we look at the code. Well, MergeSort gets called recursively on L1 and recursively on L2. So the only thing to look out for is that, so we have something like S1 is equal to the MergeSort of L1. And what's important here is the length of L1. The length of L1 is equal to n divided by 2 floor. And the only thing we should check, that we need to verify, is that the floor of n divided by 2 is smaller than n. And this works because n is bigger than or equal to 2. So yeah, I mean, actually, the floor of n over 2 is always going to be smaller than n for positive things. So this is less than n. And so by the inductive hypothesis, S1 is a sorted version of L1. And then S2 is the merge, what happens when we, or what we get from calling MergeSort on L2. And the length of L2, this is the one we actually have to be careful with. So it's everything that's not in L1. Does anybody know a different way of writing this? If it was just n minus n over 2 without any floors or anything, then indeed this would be n over 2. Yeah, but you round up. And you can check that if n is even, then taking the floor doesn't matter. N over 2 is an integer, and this is just n minus n over 2. And if n is odd, then taking the floor here means you lose a half, and then taking the ceiling here means you gain the half back. Okay. All right, so this is the ceiling of n over 2. So this is less than n because n is bigger than or equal to 2. Sort of a really common mistake when programming these things is to get this just wrong like this, and then you run your program and Stack Overflow, typically, because you get an infinite recursion. But in this case, it works out. All right, and now we come back to, so S1 is indeed a sorted version of L1, S2 is indeed a sorted version of L2, and, merge S1, S2. We argued by inspecting the code that it correctly returns sorted list containing S1 union S2, which is the same thing as L1 union L2, which is the same thing as the original input list A1 through AN. Okay. So there's what a so-called proof of correctness of this thing looks like. If you're interested in proving these things. But the reason that I'm a little bit skeptical about all of these things is there's many places here where you rely on, oh, I looked at the code and the code does this thing correctly. You're just as likely to make a mistake in looking at the code because you wrote something like L1 and L2 here instead of when you meant S1 and S2. So I don't have a lot of faith in these proofs of correctness. Usually you do a proof of correctness at a very high level, and then ultimately the code is the test. Because the code can have little mistakes in it that your proof doesn't catch. More interesting is understanding the running time of this thing. Okay, so all right. So MergeSort correctly sorts, but the question is how quickly. All right. So let's do a little example, which should be illustrative. And let's do let's take that as our input list. Okay. All right, so let's say I want to use MergeSort to sort this thing. The first thing that MergeSort does is to check if the list is of size 0 or of size 1, and it's not. So it's going to split the list into the first half and the second half. So it's going to take the first half, that's the L1, and a second half, that's the L2. And what happens next? It's going to, well, it's going to call itself recursively on the first half. So when it calls itself recursively on the first half, it's the first thing it checks is if the list is either empty or of size 1. And if it is, it's done, but in this case it's not. So it's going to split this list into two. A first half and a second half. And now it's going to call itself recursively on the first half, which is going to split this list into two, a first half and a second half. And it's going to call itself recursively on the first half. Now we get down to the base case. This is a list with only one element, so it doesn't have to do anything. It just returns that thing. So it returns the value, or the one element list 7 there. Now we're up in this invocation of MergeSort. So it's called itself recursively on the first half. Now it needs to call itself recursively on the second half, which again immediately returns a one element list containing 15. Now what happens? Yep. It calls merge, and it calls merge on this sorted list and this sorted list, and merge correctly merges these two sorted lists, and it returns the sorted list containing those two elements. Okay. Now we're back up at this invocation of MergeSort, which has already sorted L1, its first half. Now it needs to recursively sort L2, which it does, and L2 has size 2, so it gets split into a first half and a second half. The first half is recursively sorted, which has only size 1, so it immediately returns. Now up here it needs to finish sorting the second half, which it does. It has size 1, so it immediately returns. And now it merges this sorted list and this sorted list. And returns this thing. Okay. Now we're back up at this place where we have sorted the first half, we've sorted the second half, and now we call merge to merge those two things. First half is sorted, second half is sorted, and if we did everything right with our merge algorithm, then it's going to correctly merge those and give us back the value that we'll return, which is 2, 4, 7, 15. And now we're back up at the top. This invocation of MergeSort has finished sorting, recursively sorting its first half. Now it has to recursively sort its second half. And the second half gets split into 2. The first half of that gets sorted, and that gets split into 2, 9, and 6. First half of that gets sorted, which is trivial. It immediately returns just one element. 6 also is trivial. When we sort the second half, we get 6. And now we merge these two sorted lists, the list containing 9 and the list containing only 6, to get back the sorted list 6, 9. Now up here, we've recursively sorted the first half. It's time to recursively sort the second half, which splits it into 2. This is trivial. Then it sorts the first half, which is trivial, sorts the second half, which is trivial, and then it merges those two sorted lists, 8, giving us back a sorted list containing these things. Finally, we are back up here. This invocation has sorted its first half of its input, it's sorted the second half of its input. It calls merge to merge those two things, which, if merge is correct, we'll do 6, 8, 9, 10. And then finally, we're back up at the top, and we have sorted the first half, sorted the second half. Now we just need to merge the two, and we're done. And now it's actually, I myself have to think about how the merge works. So it's going to be 2, 4, then 6, then 7, then 8, 9, 10, 10, and then finally 15. Okay. So it's clear how this algorithm works, and it's, I mean, these things are a little bit, well, not terribly long. I mean, it's not a huge picture that I've done here, but sometimes it's important to actually work through these things in order to really understand what's happening with recursion. Sometimes it seems magical, but when you work through these things this way, you see, okay, this is exactly what's happening. And not only that, but you also see what order things are happening in. In fact, if I ask you now, so MergeSort does some comparisons, right? Sometimes it compares, it's always, in merge, it's comparing things. So in this list here, what are the first two items that are compared? 7 and 15. So no comparisons happen until you get all the way down to trying to merge, in this step, trying to merge the output of the two, of the first half and the second half. That's the first time a comparison gets done, and it's between 7 and 15. Okay? And you can convince yourself, actually, that's always what MergeSort is going to do, ultimately, is compare the first two elements of your list. All right. Let's say other things to note about this tree. Maybe the depth of recursion is important here. So if this is our initial call at depth 0, then there's some recursive calls that happen. So here we have depth 1. Here we have depth 2. And here we have depth 3. Okay. All right. So this gives us some baseline for what's happening, or what this thing looks like. And actually, this is going to guide us now to figure out really how we can analyze the running time of this. So so here's what we're going to do. So we want to analyze running time, and we don't want our analysis to depend exactly on what kind of machine it's running on. So we don't want an answer that's in milliseconds or microseconds or even number of instructions. We want something that captures the essence of it and gives us a sort of the number of comparisons. Okay? So where did the comparisons happen in MergeSort? So I've just erased the code, but where do different input values get compared? Is it actually in the MergeSort function? No, it's in the merge function. So this happens in the merge function. Okay. So this merge function so it had you gave it this list S1 and this list S2, and there was a loop there. Yep.
Sorry, just to be clear, you mean comparisons of elements, not size?
Yeah, I mean comparisons between different values inside the, so different elements of the input list. Yeah. So not comparing if the size of the list is equal to 0 or the size of the list is equal to 1. Okay. So if I give it these two lists, how many comparisons does it do? So if I give it two lists of size 5, let's say, each of size 5, how many comparisons does that merge function do? Yep. if I give it two lists of size 5, so maybe these are lists like 1, 3, 5, 7, 9, and 2, 4, 6, 8, 10, then what happens is, well, these two elements are compared, and 1 is the winner. Then these two elements are compared, and then 2 is the winner. Then these two elements are compared. 3 is the winner, then these two, and 4 is the winner, and so on. So for each of these elements, 1, 2, 3, 4, 5, 6, 7, 8, 9, I had to do a comparison, right? There was a real contest there. And the last element, 10, actually there's no comparison because 10 is by default the winner. So 10 is by itself. So this merge function, the number of comparisons is size of S1 plus the size of S2 minus 1. And that is at most. Okay. So if I give it these two lists, size S1 and S2, then the number of comparisons is at most the size of S1 plus the size of S2 minus 1. Yep.
But this is only when we compare already sorted list. We had comparisons before. Should we count them too?
Well, all of the comparisons ultimately happen inside the merge function.
And like in merge, we can merge the first two elements and also merge.
Oh, yeah. So we want to count all the comparisons that happen in the merge here, plus 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 all of those things. Okay? And this minus 1 here kind of annoys me because it'll just get in our way, and usually it doesn't mean much. So I'm just going to say the size of S1 plus the size of S2. So I'm not going to tell you exactly what the number of comparisons is, but I'll tell you that it is at most this much. And I can't tell you exactly what the number of comparisons is for a couple of reasons. One is because I'm lazy and I don't want to include this minus 1 in my calculations. But the other one is the actual number of comparisons done here isn't always the size of S1 plus the size of S2 minus 1. Because remember, if I gave it this input, if this was L1, and this was L2, then what happens here is 1 wins, then 2 wins, then 3 wins, then 4 wins, then 5 wins, and now there's no more comparisons to do. We just append all of L2. So in that case, we would only be doing size of S1 comparison. So it's somewhere between the size of S1 and the size of S1 plus the size of S2 minus 1. But it's never more than this, that's for sure. Okay. And typically when we analyze algorithms, we don't want to say, oh, it might run this fast, because that's not a really useful guarantee for anyone. So we're not interested in how few comparisons it might do. We would like to say it never runs slower than this. And in this case, this merge function never does more than this many comparisons. So that's a safe thing to say. Okay, so we'll do two things now. One is we'll assume n is equal to 2 to the k for some integer k bigger than or equal to 0. That's good. Why are we doing this? We're doing this because the book does it. If you want to not do that, you can go and read my book on data structures instead, where we don't assume that. But ultimately, why do you assume that n is of the form 2 to the k? It's because it makes it a little bit cleaner, because these floors and ceilings here are a problem otherwise. Or they're not a problem, but they mess up your calculations without actually teaching you much more about the problem. So when n is a power of 2, then every time you take n and divide it by 2, you get an even number. And then you can divide it by 2 again and you get an even number until eventually you get down to 1. Okay, so we're going to assume this. And let's say let f of n equal number of comparisons done by MergeSort on input of length n. So since MergeSort is a recursive function which recursively calls itself on inputs of length of smaller length, seems like f of n here is going to be a recurrence equation. Okay. So if I want to write f of n as a recurrence equation, that means I need a base case for my recurrence. And what's the base case? So base case is when n is 0 or n is 1, in which case how many comparisons does MergeSort perform? 0. Doesn't do anything. Just returns whatever it was given. Otherwise, n is bigger than or equal to 2. How can we write this as a recurrence? So it first calls itself on the first half of the array, right? So whatever we do number of comparisons we do when trying to sort an array of length n, it's going to be the number of comparisons we do when we sort the first half, plus the number of comparisons we do when we sort the second half, plus the number of comparisons we do when merging. So this is number of comparisons we're going to do when we sort the first half. The first half is an array of length floor of n over 2. The second half is an array of length ceiling of n over 2. And to merge those two halves, we call the merge function with an array of length, a sorted array of length floor of n over 2, a sorted array of length ceiling of n over 2. So that means together those two things have length n, so that's our S1 and S2 here. So that means that the size of S1 plus the size of S2 is actually n, and we'll use this estimate here for the number of comparisons. So that means it's whatever happens recursively plus whatever happens recursively plus n comparisons to merge those two things. So actually n is an overestimate, but it's okay. It's not going to bother us. Okay? Is that clear? So far this is all honest to goodness, no hiding anything here. And the only thing that I'm going to hide or that I'm going to gloss over is these floors and ceilings. And we'll get to gloss over those because we're going to assume n is a power of 2. Okay? So n is 2 to the k. For some integer k is what we're assuming. That means k here has a name. So what is the value of k in terms of n? It's log base 2 of n. All right. So now if we use that assumption, so we're saying f of n is less than or equal to 0 if n is less than or equal to 1, and it is less than or equal to 2 times f of n divided by 2 if n is bigger than or equal to 1, right? Because if n is even, then floor of n over 2 and ceiling of n over 2 is the same, and so this is just 2 times f of n over 2. Plus n, of course. Plus n. Okay. So in a later course, you'll learn to solve these things instantly by applying some theorem, but for now, we'd like to figure out some way we can get an intuition for them. And in fact, that theorem that I'm talking about is called the master theorem. Usually people forget it and they use their intuition ultimately anyway. So let's just do what we did there, but with some fictional, some more abstract version of this picture here. So at the top level, we start with an input of size n. Okay. And we split that. That's what this function says. We split it into two inputs of size n over 2. And this one is split into two inputs of half the size, and so on until we somehow get to the bottom of this thing. Now, if you don't like pictures of trees like this, you can write this as f of n is equal to, let's take this n, get it out of the way so I don't forget it again, plus 2 times f of n over 2. That's equal to 2 plus 2 times, so each of these things of size n over 2 gets split into two things of size n over 4. Plus, I should be more careful. So just take the definition of f of n and apply it now, but with the value n over 2 here. So you get a n over 2, you get a n over 4 here. There's your n over 2. There's your 2 times n over 4. Okay? And we can write that slightly differently. 2 times n over 2 is n, and 2 times 2 is 4. It looks like that. And what happens next? Well, we can apply the definition of f here. That's n plus 4 times, what does the definition of f tell us? Well, that says that it should be n over 4 plus 2 times f of n over 8. And we can do the same thing again. This is now n plus 4 times n over 4 is n plus 8 times f of n over 8. Does anybody see the pattern that's developing here? Okay. So you get a bunch of n's here, And if I do this again, I'm going to get another n, and now it's going to be 16 times f of n over 16. And if I do that again, I'll get another n, and it's going to be 32 times f of n over 32. Or if you prefer this tree picture, what I'm really doing is saying at the first invocation, which is not recursive yet, by the time when I finish this, in order to finish this, I'll have to do n comparisons when I merge the first half and the second half. That's what this number n really represents here. And now, before I do that, I have to recursively sort the first half and recursively sort the second half. Now, when I recursively sort the first half, the last step in that process is to merge these two things, which is going to require n over 2 comparisons. And the same thing, when I recursively sort the second half, the last step is going to be to merge these two things of size n over 4, which is going to take n over 2 comparisons. So actually, this thing that we're expanding here is really this thing. So it's the recursion tree. And the really nice thing about it is, well, this level here, the number of comparisons is n. This level here, the number of comparisons is 2 times n over 2. Here's where that's showing up, right there in that formula. So 2 times n over 2 is n. And at this level, it's 4 times n over 4. So that's where this is showing up. And this is 8 times n over 8. That's where this n is showing up. And so basically, all I have to do is add up all the numbers that are in this tree. I know that each level adds up to n. So the only question is how many levels are in this tree. Okay. The lowest level will be, well, let's take a, the lowest level will have n terms in it, but really how many levels are there is the question. Yeah. Yeah, exactly. Okay, so let's look at this again, still more abstractly. We start with n, then we have n over 2 and n over 2. And then we have n over 4, n over 4, n over 4, and n over 4. And in general, if I go down, I will have this will be n divided by 2 to the I. And now this is with, I equals 0, I equals 1, I equals 2. And in general, it's going to look like this, right? So n divided by 2 to the I is the number that I see at depth I in this tree. On the other hand, I stop as soon as this thing is less than or equal to 1. So that means that n divided by 2 to the I should be bigger than or equal to 1, which is the same thing as saying that n is bigger than or equal to multiply by 2 to the I, which is the same thing as saying that log n is bigger than or equal to I, or rather, I is less than or equal to log n. So the number of levels in this tree is only log n. Okay. All right. So that's somehow some intuition. And so that should tell us, or that makes us guess, that the answer here is going to be n log n times log n. So we better check that. And we have to be quite careful, or when we argue using these sort of pictures of trees, we have to be sort of careful with what's happening at the very ends here. Like at the bottom level, when I is equal to log n, that's a bunch of subproblems of size 1, right? It's just little singleton lists. No comparisons actually happen down there because those just return immediately. So we just make sure we're not off by 1, and the best, safest way to do that is to just now use induction. So the claim is that for n equals 2 to the k integer bigger than or equal to 0, MergeSort does at most n log n comparisons. And equivalently, that's saying that f of n is less than or equal to n log n, and the logs here are all base 2. So we need to check that for our base cases. And now, because n is equal to 2 to the k, this base case, and k is bigger than or equal to 0, this base case n equals 0 never happens, right? We never end up with a subproblem of size 0, okay? That's good. So let's check the base case. N equals 1, which means that log base 2 of n is equal to 0, and MergeSort does 0 comparisons. 0 is equal to 1 log 1 is equal to 0 comparisons. So the base case checks out. And now assume true for arrays of length 1, 2, all the way up to n minus 1. In fact, we don't need all of those, but that's fine. And now prove for n. So there, and this is for n bigger than or equal to 2. So there we have f of n is equal to, let's use the definition that we have, 2 times f of n over 2 plus n. Let's use our inductive hypothesis here. So that says that to do the value of f of n over 2 be n over 2 log base 2 of n over 2 plus n. We can simplify that still a little. That's going to be n log base 2 of n over 2 plus n. Are we there yet? Does anybody know how to proceed at this point? So in this formula, I've got this annoying extra n. On the other hand, I have an n over 2 inside the log. I don't want either of those things. So log base 2 of n over 2. Yeah. So remember, logarithms when you have log of a over b, that's actually log of a minus the log of b. And in this case, b is 2, which works out really nicely because log base 2 of 2 is 1. So that thing is log base 2 of n minus 1. All right, so let's go back to this formula that we were seemingly struggling with. We have n log n over 2 plus n. Well, now we know that that's n times the log of n minus 1 plus n, which is n log of n. We multiply through by the n's, minus n plus n, which is n log n. Okay. Bring it. And so a couple of things about that. So one is, well, what's our obsession with comparisons to begin with? Well, if you look at all of the other stuff that MergeSort does, it splits a list into two lists, and then it recursively sorts each of those things. But then it has to merge those two things together. And the number of comparisons that it does is actually, or at least we're saying that it can do, is just the length of those two lists that it's putting together. So that means that the number of comparisons that it does, they are as much as the work that went into creating those two lists. Okay. So we're not, so everything that MergeSort does, you can say, well, the splitting this list into two, well, that's not more work than just the comparisons that are done when you sort those, or sorry, when you merge the two resulting sorted lists. So ultimately, everything in MergeSort you can charge back to some comparisons, and so this is really the running time. I mean, the number of instructions executed by MergeSort is some constant times this thing. Okay? I don't know what constant, because it really depends on exact details of your implementation, what kind of machine it's running on, and so on. But it's it's proportional to n log n. And the way we typically write that is with some statement like the running time of MergeSort on a list of length n is O of n log n. And if you remember back to where you learned the definition of this thing, well, it's actually a set of functions, but the interpretation is it's not more than some constant times n log n for big values of n. Okay. And, what does that look like? Well, if you take n is 2 to the 20, so that means that's approximately 1 million. So if I want to sort 1 million elements, then the amount of time that I spend, or the number of comparisons that I do, is about 20 million. That's not terrible. Right, 20 million is not a huge amount to ask a computer to do, and it's especially not a huge amount to ask it to do if you're asking it to sort 1 million things, then 20 million operations is not outrageous. But even if you take n is equal to 2 to the 30, so that's about 1 billion. So now you're talking about something that, depending on the size of the data, can be just basically reaching the amount of RAM you have in your machine, right? This is a gigabyte if this were, each of these was a byte. Then n log n is only 30 billion, which is not bad at all, right? I mean, think of your machine as executing 1 billion operations per second, so it might take 30 seconds to sort 1 billion items. That's pretty good. I mean, you can't really do much more than that because you'll run out of memory before then. All right, so that's a good place to stop for today.